This is the first installment in the lecture series DC circuit analysis. In today's lecture, we will primarily go over node voltage analysis, namely nodal analysis and supernodes. Before we analyze nodal analysis, let us first look at Kirchhoff's current law. Kirchhoff's current law states that the currents which is entering into a node is equivalent to the currents which are exiting from a junction or a node. So if we consider this node here, there are so many branches of this node, and there are some currents which are entering and some currents which are exiting. So the Kirchhoff's current law says that the sum of the currents which is entering a particular node is equal to the sum of the currents exiting. So this is 1, 2, 3, 4, 5, then 1 plus 2 plus 3 is equal to 4 plus 5. Obviously these are currents, not numbers. So Kirchhoff's current law is just a restatement of the law of conservation of charge in circuit form, along with the added point that there cannot be any charge storing devices in the circuit. Because this is a DC circuit analysis and there are only resistive elements, DC sources and dependent voltage sources, but still DC sources, there cannot be any charge storing devices in the circuit. Hence, Kirchhoff's current law will apply in the form which I have mentioned here. The total charge which is entering into a junction is equal to the total charge exiting a junction. Now that we have that out of the way, let's look at what is a node. By the way, this qualifies as a node. This is a node. Why is it a node? Because there are more than three branches which are going through this node. There's this branch, this and this. If there are three or more than three branches which are exiting a particular node or a particular point, that point is called a node. So for example, in this circuit, this point is a node because there are there are four branches in this node. If there was one branch here, then this is also would be considered a node because there are three branches, this and this. So B would be considered a node. But this point here, this point is merely a junction because there are only two connections over here, this connection and this connection. Hence this is considered a junction. By all the nodes are junctions, but all the junctions are not nodes. So now let's get into node voltage analysis directly. So what is node voltage analysis? It's basically a method to solve the circuits so that you can obtain the branch current in each resistor, and equivalently after you find the branch currents, you can find the power which is dissipated in each resistor or resistive element which is present in the circuit, or else you can find the currents which is passing through multiple loops or meshes. So node voltage analysis is one of the many methods which is used to find the branch currents. There are other methods like mesh analysis, superposition and network theorems which are used, and you can also use network reduction to find the equivalent currents. So the point is that any resistive circuit, purely resistive circuit, can always be solved using KVL and KCL. I will not explain what KVL is now. We look into that in the second installment when we analyze other methods. But using KVL and KCL, we can solve pretty much any problem which is consisting of purely resistive elements in a circuit. But do we do that? If we wantonly apply KVL and KCL in multiple loops, like if I consider a circuit over here which has so many loops, it has a very large amount of loops. If we try to apply KVL or KCL in all of the loops, we would obtain several equations, and these equations would be very hard to solve. But in nodal analysis, we just observe two nodes in this particular network. These are also nodes, but because they are at the same potential, they are not considered. So with just two nodes, we can solve the entire branch currents. But if we applied KVL and KCL to everything, then we would end up with several equations. So that is why we use these methods which provide an algorithm basically to solve the problem. So we look at node voltage analysis algorithm. So in order to understand the algorithm, we first look at a circuit here. Let me draw one. something like this. Yes. So what are the nodes in this circuit? Clearly there are only two nodes, which is A and B. So the first step in the algorithm, identify the nodes. The second step in the algorithm, designate a reference node. We designate this B, let's consider this B to be the reference node. So the reference node is always grounded and it is considered to be at zero potential. So find the reference node or designate a reference node. Then solve KCL equations in the non-reference nodes. So which is the non-reference node here? A is a non-reference node. We solve the KCL equations in non-reference nodes. KCL equation in non-reference node. So this is just the algorithm of node voltage analysis. Let's take some values. Let's consider all the resistances to be 1 ohm each and the voltage source to be 2 volt. Okay. So what are the currents which are being pushed into this node here? This current is being pushed into A, this is also being pushed and this is exiting out. So we try to find the current, the branch current in 1 ohm when we consider this A, the potential at the point A to be VA. We consider the potential at point A to be VA, and using this potential as a variable, we try to find the currents in each branch. So this current I1 which is entering, I2 which is entering and I3 which is exiting. So what is I1 equal to? So clearly in this 1 ohm resistance, we have the potential here at 0, these are the same potential and this is at VA. So the 1 ohm resistance is VA by 1, VA minus 0 by 1, which is VA by 1. In this 1 ohm resistance, we have 2 volts difference here. This is 2 volt, we consider this to be a 2 volt potential. So VA minus 2 divided by 1 is equal to I2, and I3, this is VA itself, this is 0. So I3 is VA minus 0 by 1, and by KCL I1 plus I2 is equal to I3. Therefore VA minus 0 by 1 plus VA minus 2 by 1 is equal to VA minus 0 by 1. This is the equation and we solve for VA using this equation. So what do we obtain here? VA, what are the connections? I3 is not VA minus 0, it is minus VA plus 0. So 0 minus VA by 2. I3 is 0 minus VA by 2, because since this is at 0 potential and this is at VA, we go from here to here because the connection, we look at the connection, this negative, positive, positive, negative. So the push is from here. So in reality, since we assumed that this current direction would be in this direction, but the current direction is actually coming in this direction. So the signs are reversed. So 0 minus VA by 1 is equal to I3. So we obtain VA by 1 plus, let me erase this here. VA minus 0 by 1 plus VA minus 2 by 1 is equal to 0 minus VA by 1. In other words, VA by 1 plus VA by 1 plus VA by 1 is equal to 2, or 3 VA by 1 is equal to 2. VA is thus equal to 2 by 3. So the final result, this potential is 2 by 3 volts. So once we figure out this potential, if we want to find the branch currents I1, I2, I3, all you have to do is to input into VA these branch currents and you can solve for the branch currents and you directly obtain the solution. So this was a very simple example of node voltage analysis. now we can move on to a more complicated example, which is this circuit here. So let's follow the algorithm. First identify the nodes A, B, C, and there's another node here, but do we need to label this node? We don't actually, because this node and this node is at the same potential, hence it can just be considered as a single node over here. We don't need to label this particular node, so let's leave it as it is. Now what is the reference node? Now you can consider any node to be a reference node, but the best node to be considered as reference node would clearly be node C, because it is directly attached to a voltage source. So this node is the best candidate for reference node, node C. The convention is to name reference nodes as O and the other nodes with other letters, capital letters. So let's now solve the KCL equations for A and B. Clearly we can see there's a current which is being pushed in from here and exiting out from here. So let's try to find the branch currents here, I1, I2, I3. Okay, so I1 is equal to, this is at zero potential, because we know the reference node is always at zero potential, and this is at 20 volt potential, because it is directly attached to a battery which is 20 volts. So this is VA potential, this is VB potential. We assume these potentials as variables. So clearly I is equal to VA minus 20 by 5, I1. I2 is equal to VA minus 10 by 5, and I3 is equal to VB minus VA by 10. Thus when you add them up, you get VA minus 20 by 5 plus VA minus 10 by 5 plus VB, let me erase this. So we found out the branch currents with respect to A and B, VA and VB. VA minus 20 by 5 plus VA minus 10 by 5 is equal to VB minus VA by 10. The branch current, this is I1, this is I2, this is not 5, this is 10, this is I2 here, and this is finally I3 here. Okay, so if we solve this, VA by 5 plus VA by 10 plus VA by 10 minus VB by 10 is equal to 20 by 5 plus 10 by 10 is what we obtain here. 20 by 5 VA, this is VA minus 0, this is an error here, sorry, this is VA minus 0, because this is at 0 potential, right? So VA minus 0 by 10 equal to VB minus VA by 10, so there's nothing here. So this is VA minus 0. The second term, which is I2, is just the difference in potential, VA minus 0 divided by 10. So I have written it in this form now, and isn't it quite evident that you can see a particular pattern here? If you look closely, you can rewrite this as VA into 1 by 5 plus 1 by 10 plus 1 by 10 minus VB by 10 is equal to 20 by 5. So we are adding whatever are the connections in A, the connections, this 5 ohm resistance, this 10 ohm resistance, this 10 ohm resistance, and this 20 volt connection. We are adding the reciprocal of the resistances which are connected to that node VA, and we are subtracting whatever is the resistance connected between that node and the other non-reference node. We are subtracting the reciprocal of that resistance into the voltage of the non-reference node. So this, in this between A and B, the only common resistance is 10 ohms. So this common resistance is the resistance between A and B, and it is subtracted and multiplied by whatever is the voltage of that non-reference node, which we consider as a variable. So this is a pattern which is observed directly, and using this pattern, let's solve for the next equation. Also notice here this 20 by 5. This 20 by 5 is merely the current which is pushed through this 20 volt battery, divided by whatever is the resistance directly connected to this 20 volt battery. That is the right hand side here. So this is the pattern which is observed in node voltage analysis, and using this pattern you can solve the problems very quickly. So at node B, what are the resistance connections? We have this 10 ohm resistance, we have this 20 ohm resistance, and this is a 4 ampere current source. So directly we write the equation 1 by 10 plus 1 by 20 into VB, which is the reciprocal of the sum of reciprocals of the resistances connected to that node, subtracted from the common resistance 1 by 10 VA, which is the other non-reference node's voltage, is equal to whatever is the current entering into that node, and directly we can write that current to be 4. So here you can see we have two equations and two unknowns. We have equation 1 and equation 2. Let me erase this so we can write that properly. Yes, so two equations, 1 by 10 plus 1, I will write it in a better form, minus 1 by 10 VA plus 1 by 10 plus 1 by 20 VB is equal to 4. 1 by 5 plus 1 by 10 plus 1 by 10 VA minus 1 by 10 VB is equal to 20 by 5, which is 4. So we obtain two equations with two unknowns, which can be solved using Kramer's rule or can be solved using a calculator if it's allowed in the examination hall. Basically it's a matrix for equation which can easily be solved using a plethora of methods. You can use elimination, Kramer's rule, calculator, anything. That's not the problem. The problem is, or basically the method of nodal analysis is to get these equations and to get them quick. So I have shown you the pattern which can directly be applied without thinking to get the problem, rather than stopping and thinking to apply KCL or KVL every single time. You can directly apply this pattern to find the nodal equations. So we can try to solve a much more complicated example using this pattern method itself. Let's first designate the nodes. This entire setup of nodes here, this all can be considered as one reference node. Oh, this reference node, because they are all at the same potential. Then the other nodes A, B, C, these two are at the same potential, so we don't consider them. So we have three nodes and one reference node, so we have to draw three nodal equations at node A. At node A, what are the equations? What are the connections? We have a 10 ohm connection, we have a 10 ohm connection, a 4 ohm connection, and 5 ohm connection. So 1 by 10 plus 1 by 4 plus 1 by 5 VA. We have a connection between A and C because these two are the same potential. This is also a C. We have a connection between A and C, so we subtract that. Apart from that, we don't have any connections with 4 ohm resistance does not have any connections with C. So this is it, 1 by 4, 1 by 10, 1 by 4, 1 by 5 VA minus 1 by 5 VC. We don't have any connections with the other non-reference nodes, so we leave that as it is. That is equal to the current which is being pushed, which is 5 divided by whatever is the current here, so that's half ampere. These are 1 ampere current sources. They are not labeled, they are 1 ampere current sources. Now at VB, at node B, what are the connections? We have a 12 ohm connection, erase these. We have a 12 ohm connection, an 18 ohm connection. We have this 1 ohm current source connection, and anything else? No, nothing else. So 1 by 12 plus 1 by 18 VB. We have a common resistance connection between B and C, so minus 1 by 18 VC is equal to we have a direct current source which is leaving the circuit, so minus 1, because we consider currents which are being pushed into the circuit as positive current, and current which is leaving the node, pushed into the node is positive, leaving the node is negative. So this is our convention which we consider. So that's the node B problem. Now the equation for node B. So we have two equations and we have three unknowns, so we need one more equation, node C equation. At node C, the connections, we have a 5 ohm connection, we have a 2 ohm connection, we have a 9 ohm connection, we have a 18 ohm connection. Here we have 4 connections. So 1 by 5 plus 1 by 9 plus 1 by 2 plus 1 by 18 VC minus 1 by 18 VB minus 1 by 5 VA is equal to what current is entering, which is 1. A current here, a current source is entering into node C, so that's 1. So you see that we have three equations and we have three unknowns that can be solved using matrix theory. So now we look into a new type, a new sub concept of nodal analysis, which is called supernode. So let's understand why supernodes exist. First of all, let's try to solve this problem. This is not 4.7 kilo ohm, this is 1 ohm resistance. So let's designate the nodes. We have A, B, we have one common ground node. So A and B are the two nodes. We try to solve the equation and see what happens when we attempt to solve the equation here. At node A, we have what connection? We have a 1 amp current source entering, we have 1 volt current source pushing, and we have a leaving here. So we have VA minus 0 by 1 plus V1 is equal to what? This 1 volt is divided by no resistance. There is no resistance in this branch, so we get a null equation. We get an equation which is unsolvable because the resistance here is 0, hence it becomes infinity, which cannot be solved. So this is the idea, this is the reason why we have supernodes, to be able to solve, to be able to clear up this conundrum. So let's consider a supernode is when two nodes are attached only to a voltage source, then those two nodes can be combined into a single node, which is called a supernode. So why supernode is allowed is because at this particular node, whatever the currents which are entering, the current which is entering is also entering due to the current which is coming through this node. So if the current here through coming through this node at the end of everything is I, then that current itself will enter into this A. So we can consider the node to be 1 and solve for one node equation using KCL and directly obtain the solution. So how to solve this supernode problem? First we consider the two nodes to be a single node, and we can take any of the two nodes. I will take node A. At A, what are the currents? A current pushed through here to push through here, so we have VA by 1 plus 1. Then we have a current which is being pushed through B's, whatever the B's currents, what are they? We have this is at 0, so this is we consider this to be VB minus 2. So plus VB minus 2 by 1. In this, the current which is being pushed through this 1 ohm resistance, VB minus 2 by 1. The current which is being pushed through this resistance is VB by 1. So the total current which is adding up from these two is this resistance, and that is adding up from this resistance, and finally all of these resistances are being added up, all these currents are being added up, and it's amounting to one single current, which is this minus 1 over here. So this is a final addition. So what do we obtain? We get VA plus 2 VB is equal to 1. So this is equation number 1. So now for equation number 2, it is very directly observed that VB minus VA is equal to 1, is it not? This is the point VB. If you use KVL, you can go from here to here and the voltage rises 1. If you go from, no, it's not VB minus VA, VA minus VB. VAB is equal to 1, which is equal to VB minus VA. Yes, this is correct. VB minus VA is equal to 1. So if you solve 2VB minus 2VA, if you subtract them, you get 3VA. In this specific problem, VA is equal to 0. Similarly, VB, if VA is equal to 0, VB is equal to 1. In this specific problem, because of the current which is entering, which is just 1 over here, and this voltage source is 2, final result VB is equal to 1 and VA is equal to 0. So that is the super node problem. With this, we will end the first installment of the lecture series in DC circuit analysis. In the next class, we will attempt to do mesh analysis and super mesh analysis and solve the problems related to them.